Etienne, and this is Gregory, and today we'll present to you the problem number 5, water dancing ball. So in this problem, we have to investigate the motion of the ball on a hard and flat surface heated by a jet, and investigate the dependence on the relevant parameters. So, for small jets, the axisymmetric position will be the equilibrium position. But as we deflect the ball starts to oscillate, but these oscillations will be damping. But for other parameters, their amplitude of oscillations will grow up and saturate on some level, and thus we will observe the self-oscillations. So here is our structure. We'll talk about the qualitative explanation, then about the period of oscillation, about the model of water flows, the period in experimental in theory, then about the amplitude of oscillation, experimental of, explanation of stabilization, theoretical, and experimental investigation. So, first we will talk about the forces acting in a ball. So first one is the pressure force from a water jet, which loses its normal projection of the momentum, and this force will push the ball out of the jet. And after the collision, the water flow falls around the ball, and the direction of its momentum will change. And thus, we will have the force that acts on the water flow. And according to third Newton's law, we will have the force that acts on the ball. And this force will pull the ball back to the jet. And thus, we have the net force, and this net force will be the restoring force. And we can think that this force depends just on the position of the ball, but in fact, it also depends on the motion of the ball. But because of the motion, we have a redistribution of the water flow, and thus more water will go on here is on the right side, and thus the net force can change its value or even its direction, and this means that instead of damping, we will have the pumping of energy into oscillations.
So describe this mechanism theoretically. We first of all see from experiments that in our problem ball rolls on the surface. So further we will investigate the torques acting on the ball relatively to the contact point to eliminate friction force from the equations. As we mentioned, the force acts to force. It's a pushing force and its torque. And the torque from each point on a ball, and we need to find this force is acting from each elementary fragment of the water which flows around the ball. To do this, we will divide the whole problem on two parts. At first part, we will investigate the flow of water on a flat surface. On a flat surface, and then we will investigate the flow of this water around the ball. To do this, we used, instead of exact solution of Navier-Stokes equation, we used empiric result for the redistribution of mass rate in different directions, which is defined by the Pauling angle and the polar angle on the surface. And here, on this animation, you can see how this flow changes with the change of the Pauling angle. You can see that thickness of the right side increases and the left side decreases. And so, as we know the distribution of mass rates, we can find the force acting on a ball. This force, as we mentioned, is a force due to change of the direction of the momentum, and so it's a centrifugal force. It's a force which is opposite to the centrifugal, which acts on each part of water. So this change of pressure causes the motion of a ball, and as we know the thickness of the layer from the distribution of the mass rate in different directions, we from geometrical consideration can find the torque acting on a ball, and so on this animation you can see distribution of these torques and the total torque, which changes as we change the Pauling angle, which shown on this animation. And indeed, as you can see, the total torque changes, also changes the distribution of torques. And on this plot of the dependence of the torque on the inclination of the ball, you can see that for small deflections, the torque is negative, which leads to the return of the ball in the jet. And for higher, there is positive, which leads to the push of the ball out of the jet. And we plotted the dependence of energy of this inclination angle. Indeed, as you can see, for some region we observe finite motion, and for some infinite motion, where we can define the period of these oscillations by integrating the by integrating this equation. So now let's discuss about, we mentioned in the preliminary observations that relative motion may strongly change the type of motion of the ball. Now let's discuss to what it leads. We can divide the relative motion of a ball on a motion on two projections of the velocity at contact point. On the normal velocity, which leads to the ball goes out from the jet, and so the relative velocity decreases. But tangential motion of the surface leads to the redistribution of mass rates because of the friction of water and ball, and it leads to the change of the force which causes the motion of the ball. So to find this redistribution of flows, we use program Karazin multiphysics, where we set such a geometry of a problem. We set a ball, we set a tube from which we investigate the motion of water, and we set the two regions where we solve the Navier-Stokes equation of motion. In first region, there is we choose the mesh to be much higher because around this region there is a flow of water, most flow of water, and in the airs we choose mesh to be much lower. And we used KE turbulence model with the solve of Navier-Stokes equation, and here you can see the result. Indeed, as the water moves, it stops around the ball, as we mentioned in the previous part. Then we have a distribution of flows. You can see that to the right moves more water than to the left. And so, using this, we can, by integration of force, we can define the full force and full torque acting on a ball. And here you can see the dependence of this full torque acting on a ball on the deflection of the ball with the relative motion. And as you can see, for small deflections, this torque is negative, and for higher one, it is positive, which leads to the change of the force acting on it. And we solve equation of motion with the stationary torque, which we found before, and with the time-dependent torque. And here you can see the typical solution of this differential equation. And as you can see on a phase plane, for small initial deflections, the ball increases its amplitude, and for higher, it decreases its amplitude.
Okay, to verify it experimentally, we built such a setup. We used the limerizator, also we used holders to hold the camera to field all the process, and also we used different balls. So here you can observe our self-oscillations, and to make I'm sorry. Okay, here you can see the motion of this ball as on the experiment, and we can observe how the oscillations become constant. Comparing it with our theoretic theory, we can see a good correlation. Here you can see the same for damping oscillations, how the damping oscillations become the constant, as we said in our theory. And so now we can talk about the dependence on key parameters. So as we change the velocity of the jet, the time of the set rate of the time of stabilization of the oscillations also changes. So here you can observe the amplitude of oscillations, how they become constant, while their frequency become higher and higher. And here you can observe our oscillations in different types of our oscillations, and we change their mass rate, and thus because of the changes the mass rate, we change the diameter of jet, and thus we find the dependence on this. So here you can observe their dependence on their mass rate of amplitude and frequency. Thus, as I said, we changes a lot of balls, and we change their radius, and as you can see, for smaller radius, we have smaller amplitude but higher frequency. So in our problem, we found the distribution of water flow. Also, we find period and experimental in theory, and also we make the experimental verification where we we find their dependence on relevant parameters. Thank you for your attention.
Thank you.
So, hello everybody. I am Nicholas. I'm from the SYS team. I will be opposing Ukraine on problem number 5. Okay, so we are asked, okay, well the problem statement, this is for the 2D motion of a ball. We see it oscillating under the jet. You guys have already gone through the mechanisms behind this force. So what we would explain, okay, so we would expect an explanation behind the mechanism of oscillation. You guys have clearly stated that. We would expect to see some dependence of this oscillation on the different parameters of the system, the radius of the ball, the mass of the ball. For instance, for the stream parameters, we would expect to see something with the radius of the stream, the velocity of the stream, perhaps viscosity and surface tension could also be important. And then we would like to see some parameters dependent on the surface, for instance, the elasticity of the surface and the friction of the ball with this surface. And then perhaps we could decide if the motion of this ball is harmonic or chaotic, since it clearly has to do something with initial instabilities. Okay. So the reported topics were a demonstration of damping versus increasing oscillation, which then stabilized. These were the 2 conditions that they considered. There was a force diagram, which was pressure force, thermal force, and so this is the mechanism behind this initial oscillation. Then there was analysis of the torque due to the fluid. Then we had the flow model in a plane, which was then applied to the surface of the sphere. And effective. Yes, considerations with the Navier-Stokes equation. Then we had the study of the amplitude of oscillation as a function of a few parameters. And most of the parameters that we considered were just velocity, mass rate, and different balls, radius, and mass. So, first of all, I'd like to congratulate you because this was a very, very complete problem. So yeah, we had a complete model for a one-dimensional motion. All the questions of the statement were pretty much covered. And then we had, you had clear verification of your model in this case. Some of the weaknesses, there was no treatment of the 2D precession of the ball since the motion is not entirely stable in a single plane. So perhaps we could treat that. There was no variation of the friction of the ball and between the ball and the surface. And perhaps I just missed this, but there was no clear condition for the oscillations to start because these only happen within a certain regime. So perhaps first we could go through, okay, what do we need for these oscillations to begin? You guys went through damping motion and self-sustaining motion, but okay, what do we need to actually see oscillations? Then perhaps we could talk about the precession of the oscillatory motion in the 2D plane. To what extent did this matter? Why didn't you study it? Was it just not available at the timescales you were studying? And then perhaps we could also consider the influence of a few other parameters. So you did stream, you did radius, you did these. But then perhaps we could consider what would happen if we had a softer surface, and also if there were no friction. And then perhaps we could try to improve your experimental setup to take into account these surface parameters. And then, some further questions would just be, okay, what happens if we have no friction? And then perhaps we could do a slight modification on the problem, considering what if we had a plane that was not, well, the surface were not flat, but instead if it were like a small cone or something like that, how curved would the surface have to be to keep the ball inside the jet? Could we have some kind of coefficient of elasticity or something like that? So, okay, I guess we'll start the discussion. So could we treat this first part? What are the conditions for us to actually begin to see oscillations? What does the ratio between the jet radius and the ball radius have to be?
We investigated this in our problem. We will show it right now. We investigated how, for example, we understand that for small, for example, mass rate and small velocity, there is no oscillations. But as we try to increase it, we start to observe that. And we investigated both theoretically and experimentally conditions of...
My main question is just, what are the main parameters here? What do we need to verify?
Parameters of the jet. We verified parameters of the jet. Yeah, but here it is.
So which parameters?
Yes,
just list them to me. So we need something on the radius of the jet?
Yeah, radius of the jet.
Radius of the ball?
Velocity of the jet itself and also mass of the ball, for example.
Okay, so
it's a main parameter, I think, in this problem.
Yes, okay, so what do the relationship between these parameters have to be for us to see oscillations?
For example, for the radius and the velocity here, it's curved, and we also refined it experimentally for different diameters of the jet and different velocities of the water.
So red points we see no oscillations.
No, in green points we observe oscillations. Red we do not observe. For small velocities we do not observe oscillations.
Okay, very well. So what is this law here?
It's a law which we obtained from the simulation in our stuff. Like we solve the equation of motion, and under which we observe the exciting of oscillations.
Very well. So this depends mostly on the velocity of the water and the initial radius of the jet. This is for a fixed radius of the ball.
Yes, for a fixed ball. Yeah, and it's mass fixed also.
Okay, so we have a fixed radius of the ball.
Yeah.
And then this sort of looks like what is this, like 1 over r? Okay. So all right. So you have a clear domain where this is verified or not.
Yeah.
Okay. Now could we perhaps speak about this precessing motion? For instance, we have a jet. You characterize the oscillation of this ball in one dimension.
Yeah.
But then when you look at it from above, the ball starts to oscillate in this direction, but then it also starts to shift.
Yeah.
And is this motion regular? Is this chaotic?
Like indeed, the change of the direction of the oscillations, it's a result of some uncounted parameters. For example, ball has an ununiform distribution of mass, and so there is some kind of line around the tennis ball.
Wait, what do you mean? So you mean that this precession is due to the center of mass not being in the center?
No. In our experience, we mostly observe the rotation of the plane of oscillations, but also we observe the rotation of the ball in the
wait.
jet.
So just to be clear, so you saw that so we had a plane of oscillation, and then this plane was rotating just by an angle.
It may rotate, and also it may just incline on some angle, and it will remain the same.
Okay, but so it remains the same. So what is the time scale of this transition?
Nearly seconds 5 or 6, if it is possible, yeah.
Right, 6-second transition. Okay, and what was the cause behind this?
Some effects, for example, in the case of tennis ball, it has a line, just constructive line.
So in that case, it would be surface imperfection.
Yeah.
Okay, so if I had a perfect ball,
yeah. And
would I see this kind of motion, or would I not?
I think it will continue in plane in which you initially initiate this oscillation.
Okay, but then if I have my ball, my initial ball, and I drop water on top, there's some kind of imperfection that makes it begin to oscillate.
Yeah,
okay,
indeed.
but then so if the ball is perfectly symmetric, this still happens in one dimension.
Yeah.
Okay, then why wouldn't this happen in 2 dimensions as well? Why wouldn't I have little shifts that would then cause it to start to precess?
We are talking about the jet, like the
in the case of a perfect ball, because you said, okay, in the case of the tennis ball, you have the surface, but what would cause this in a perfect ball?
If there is some kind of turbulence, which and so the flow is not constant during the time, yes, it may somehow change. There will be some kind of force which is perpendicular to the plane, and it will I think that it will be a chaotic motion, chaotic change of the angle of oscillation of the plane.
So this would most likely be chaotic in a high reference number.
In the case of the non-perfect jet, yeah.
Okay.
And perfect ball, yeah.
Okay. Sorry, let me just remind myself of my program. Okay, so yes. Sorry.
Good afternoon, everybody. My name is Juan Manuel. I'm part of the Colombian team. I'm going to be the reviewer of the problem number 5, wireless symbol. So, again, we are going to make emphasis on the questions of the problem. They ask for the investigation of how the oscillations depends on the relevant parameters in this phenomenon. First, I want to congratulate the reporter for your excellent solution. You touched almost all the points, and here's the summary of the presentation. First, they talk about the preliminary observation of the forcing balls and the self-oscillation. Second, they approach the problem in the theoretical way, analyzing the torque, the model flow in plane, the effective potential, the period of the oscillations. They use console simulation to also do that. And at the end, they talk about the torque due to the relative motion. Then they move to the experimental verification and they compare almost all the parameters of the theory and the experiments. They talk about the damping effects, the experiments changing the diameter of the jet, the dependence on the mass rate, and finally they prove with different kind of balls. And finally they present the conclusion. Then the opponent summary, I want to congratulate also the opponent summary because they talk about really interesting topics about the physics. First, they presented the expected topics that they think are important in the solution of the problem. Then they summarize the reported topics of the reporter, and they after make the critiques of the strengths and the weaknesses of the reporter's presentation. First, the strengths. They made emphasis on the really good analysis in one-dimensional motion and the comparison that they made with the simulation and with the experiments. The weaknesses they point out were the 2D precision and the 2D analysis in general, the friction coefficient and all the parameters involved with the contact surface, and finally the conditions for the oscillation, if they are archaic or not. Finally, they give their ideas for the discussion. They think about how to characterize the motion of the ball, then the important parameters that you think are important in the theory model, the proof of the setup in order to see other effects, the zero friction case, and the minimal force to eject the ball. Now, the discussions. In the discussion part, we see these three strengths. There are clarification on the relevant parameters of the model presented by the reporter. They go deeper in the 2D analysis, and that was so great. They use a lot of visual aids in order to illustrate how they think are these phenomena important. And finally, they talk about the type of the discussion in the part of the it's chaotic or not. The weakness is that we see that they didn't address the experimental setup in that discussion. And finally, that there were no specific improvements on the theory and on the experimental setup. Now, I want to postulate these three discussion points. First, I would like to talk about more about the parameters of the contact surface, the ball, and the experimental problem. So, can you please be here, and you be here, please. I'm going to say the rules of the discussion. So, when you want to talk, you raise your hand, and I will give you the word. Okay. First, we're going to talk the contact surface. I would like to know if you know the friction coefficient of the surface and how important it is on the movement, and if you control the amount of water under the ball in your experiments, for example.
Yeah. In the case of friction coefficient, the friction coefficient defines two regimes of rolling and the slipping. In our case, as I said, for most of our experiments, we observed rolling, but also I want to say about the amount of water that if we use the surface, curved surface, there was some amount of water, and so ball rolls at the surface, and due to buoyancy force, the reaction force decreases, and also the friction force decreases. So we indeed, in this case, observed slipping for lower velocity.
Okay, so what does this amount of water depend on? Is this just on the mass flow? So if you increase the mass flow, then you have floating, and so you have less friction?
It
or
depends
what does this
on,
depend
like,
on?
in the setup which we used. For example, for most of our stops, we used such a vessel. We just turned it on another side, and so water just goes down.
So it depends on the surface?
Yeah.
Okay.
And what did you think about the changing the surface in the experimental setup?
Changing the surface. What that would be for? Could we say that for like concluding remarks? First, we should probably talk about the main problem of the class.
Okay. Now I would like to discuss the problems involved with the ball. First, the method of inertia. It's a whole ball or a complete ball. If I'm interested in notice if you use which type of materials of the balls.
We used, as I said, we used the tennis ball, which was a whole ball, and so we used the formula for momentum of inertia for a whole ball. And we substituted it into the equation of motion.
What do you think about that topic?
Well, I would just like to say, I would like to ask, what would happen if you had a very elastic ball, and for instance, so then your jet would tend to deform the ball? What kind of effect would this have on the oscillations? Would they dampen?
I think that individual shape will change in the case of very elastic ball due to the normal force, for example, like in the ball. And due to this, I think that in the case of very elastic ball, I think that the motion of ball will not be periodical because of the change of moment of inertia will not also not be good.
I would like to add something, please. Thank you. What do you think about if you need to consider if the materials absorb water of the jet and increase the mass? That's important.
That would be an extension of the problem, sure. That would be
yes, indeed. The amount of water leads to the ball sticks some amount of water with it and moves with it. And in our theory, for example, it was taken into account in COMSOL simulation. And indeed, as we increase the mass rate, this effect also increases.
So, you're talking about adhesion of water to the surface.
Yeah.
But then, I think if I understood the question properly, you meant if it's porous and it's actually absorbing water?
Yes.
So in that case, you have a mass that's, for instance, increasing in time, but like more than just surface adhesion. So what would this have? Would this have like a dilation of the period of oscillation? Sorry. So if this has a certain like porosity, then this would start absorbing water.
Okay. Yeah. In this case, the frequency of oscillations will decrease because of the increase of mass, and so the amplitude also will change. I think it will decrease.
Okay, so frequency should go down.
Now, I will talk if there is no question of if what other limitation of your model. For example, we see in some kind of experiments that when the wire jet hits the ball, there only have water in this side, but not in this side. That's taken into account in your model? That the water doesn't fill the ball?
Yes, in some cases I agree. There's actually no water in this place, but mostly in our theory, we're taking into account the small thickness of water, but in the simulation console, yes, indeed, we observe that there is actually no water. Like it doesn't go in this side because of friction. It turns to another side.
What do you think about that?
Yeah, so what would be the effect then if you increased the water to the point where you had the water going also on the other side? Would this simply diminish the oscillating force?
It depends on the velocity of motion of the ball. Like, if the velocity of rotation of the ball very high, then the friction will turn the water ball to the other side.
We have a question, please.
Yes, a question to the reporter. Who do you think is important the precession of the ball on itself?
Precision, like if we excite the rotation of a ball and it moves, or just its fast move, and so precession of the.
But we have seen that the ball rotates on itself a little bit. So yeah, how important is it in the oscillations?
Rotate itself along the vertical axis. Actually, yes. It firstly it changes the distribution of flows, because of the changes only even for not so high velocities, and then the precession effects, like just mechanical precession effects, may be observed.
So if you were saying it would change the dynamics of the flow around the ball, so would this also change the frequency in the one-dimensional case?
Yeah. In the case of in the case of rotation, which is related to the velocity of self-oscillations of a ball.
Okay.
Like
Perfect. We have a question here.
How do you think that it's possible to introduce the precession in the theory?
Well, since they seem to have a system that is quite stable, it oscillates in one plane for a long time. Possibly what could be done would be to try to characterize the plane of oscillation, so that you have the ball oscillating like this. And then so you would characterize this simply as an angle of deviation, for example, from the initial plane of oscillation. So that
What do you think about that?
Yes, indeed, it can be taken into account. Можно переключить на 3D график, у нас там we investigated, like in our theory, we investigated, I will show you the 3D plot of energy. Yes. In some time, Женя, там есть? Depending on the initial coordinates, in the case of not viscous friction, the plane of oscillations, here it is, yes. It can rotate, yes, but due to the relativity effects, this angle will change with time, I think.
Right, so this is a potential that is confining the ball to the jet.
Yes, it returns the ball to the jet for a small amplitude.
Okay.
We have a question first.
So you said that for all these parameters and all this motion, chaos is important. So maybe a statistical approach of the problem would be also.
Yeah, I understand. I said that chaotic motion may change only in the case of a turbulence jet. But in our experiment, we use laminarizator especially to eliminate this effect.
But you said also even in laminar flow, you have you don't know.
I said
maybe the axis of oscillation will change, and
I said that it's a periodical motion but not harmonical. Yeah.
Now I would like to include the description in the experimental setup. A question for you, for example. Did you control the temperature of the water, the pressure, all that parameters were controlled in your experiment?
We can try to change the temperature yes, like in this case, as we change the temperature, I expect the change of the viscosity and the surface tension. So the whole force section in a ball, I think, will change, and as we know, the viscosity decreases, so I expect the decrease of the force, and so increase of the period.
What do you think about this, and how do you improve the experimental setup too?
I mean, I think I would improve the experimental setup mainly by having, because you guys filmed it from the side, so perhaps having a clear plane and filming from underneath, then you could fully characterize the two-dimensional motion of it, and you could even do it for high Reynolds number, considering the just the phase space. Where is it in space throughout the entire motion?
On the fit in the final part of the presentation, when you fit data, you have fitted the data for the evidence on the mass and the radius and the jet radius. That fit is
maybe this one.
Okay. Those plots. That fits is in accordance with the theory, or is really the theory, or just the fit from the data?
We haven't explained the theory. As we use a laminarizator with the same cross-section area, but then the water flows and the thickness decreases. And so we, by increasing the mass rate, increasing the velocity of the motion of the water, also the thickness changed, and we measured the dependence of this thickness at contact point, depending on the velocity of the water.
Yeah, okay. That fit agree with your theory.
We have not theory for this one. We just interpolated and then we substituted it. Like in experiment, we measured the thickness of the jet. And from this interpolation curve, we found the mass rate, which we substituted into theory and found this result.
Similar question as previously, you were kind of deduced your way through the force diagram. Could you please put up your final force diagram with all the
final force section in the ball?
The force diagram where you all the different forces on your ball.
Oh, okay.
Like where you put in all your all different.
I understand. Just wait on. It was the diagram with the forces which are acting.
Just all the different forces acting on the ball.
This one.
Is that all the forces acting on the ball?
No, further we investigated the tangential forces acting on the ball at each point due to friction. And also at contact point, yes, there is height, and in simulation it was taken into account by the flowing of the water, and it flows on the surface. Yes, at contact point there is a harder mechanism which can be described in theory, but described in the simulation.
Thank you. Any other questions? Please.
And do viscosity of the water play a role here?
Yes, we think yes, because of tangential forces which creates torque of the...
Yes. So did you take it into account?
Yes, in simulation, yeah.
Thank you.
In the slide where you have the experimental data, oscillation of the how many fitted parameters do you have in your
This slide, we substituted the law of motion, but yes, there was a parameter of the increase. I will show the force. We investigated this force, but we From theory we found coefficients, but we fitted them to get much higher precision of finding of the period and the amplitude. Like we fitted them further because of, for example, the viscosity may change during the experiment and other parameters. Like we solved the theory, it diverged, like we haven't get the frequency so good, like it was a little bit higher. And we fitted it to use them in further experiments. In user further correlation with the theory experiment. Yeah.
So for your experimental setup,
Yeah.
but how did you control your initial conditions for each of the experiments you run?
For the velocity, as I mentioned, we use linearization. Может, покажешь там, если yes, we'll show how it's based. Like it allowed us to get very stationary flow with very close to the same thickness of the cross section and nearly the same velocity, using which we indeed control the initial parameters of the flow. So we don't have photos in presentation, so.